Thank you for listening to my talk today on the impacts of assimilating infrared sounders from geostationary orbit. My name is Erica McGrath-Spangler, and please feel free to contact me with any questions you may have. First, I need to acknowledge my co-authors, Nikki Privé, Bryan Karpowicz, Isaac Moradi, Joel McCorkel, and Will McCarty. In general, the overall goal of numerical weather prediction is to enable better decision-making. We want to know if our flight will be delayed, we want to know where to ship snow shovels and umbrellas this week, and we want to know whether we should plan an outdoor picnic or a trip to the museum. These decisions require a good forecast, and a good forecast requires good observations of the atmosphere and its processes. NWP systems ingest both conventional and satellite observations and combine them with a global model through data assimilation to initialize forward-in-time forecasts. Conventional observations, like radiosondes and ground-based stations, are spatially irregular, and NWP systems use satellite observations to fill the void. This has been so successful that Southern Hemisphere forecasts are now as skillful as those in the Northern Hemisphere, even though fewer conventional observations exist there. So why should we use hyperspectral infrared observations from geostationary orbit in particular? Low Earth orbit hyperspectral radiances from instruments such as CRIS, AIRS, and ISDA have become essential to numerical weather prediction because they provide high vertical resolution temperature and water vapor information. Unfortunately, the polar orbit means that they have limited horizontal and temporal resolution. In addition, there are large orbital gaps, and it's difficult to view gaps between clouds. The twice-daily passes mean that these instruments are incapable of monitoring rapidly evolving phenomenon that change on the subdiurnal timescale. On the contrary, a geostationary sounder would fill in a lot of these gaps with consistent observations over the observed region with a temporal frequency on the order of minutes instead of hours, while maintaining the vertical resolution of the LEO sounders. Because of their potential, the World Meteorological Organization envisions at least 5 geostationary hyperspectral IR sounders by 2040 to create a global ring of observations. The U.S.'s answer to this is the Geostationary Extended Observations GeoExo program, with the proposed sounder GXS on board. The study presented here examines the impact of GXS plus 3 other international sounders. This will allow improved horizontal, vertical, and temporal resolution of observations and allow more opportunities to view between clouds and observe phenomena with a lower data latency. The global coverage from a single 6-hour assimilation window will improve from the first figure to the second, with geostationary IR sounders indicated in the pink colors, represented by the locations of current and planned sounders Himawari, GEARS, MTG, and GXS, moving from right to left. In preparation for GXS, our group examined the impact that can be expected from a ring of geostationary sounders using Observing System Simulation Experiment. An OSSI includes 3 major components. The first is a nature run. For these experiments, the nature run can be considered the truth. We use the GMAO nature run with a 7-kilometer horizontal resolution, 72 vertical levels, and a 30-minute temporal resolution. The second component is the observations. We simulated global observations from the nature run to resemble and statistically imitate the real observations. This is done by sampling the nature run at the spatiotemporal locations specified by real observations from June to September 2020 and added realistic errors. The final component is the data assimilation system used to represent the NWP system. For this, we used a hybrid 40N-VAR GSI system, the Global Earth Observing System Atmospheric Data Assimilation System, at approximately 1/4 degree resolution in the analysis, and coupled to a forecast model. This is considered a fraternal twin experiment. As part of the OSSI, we simulated geostationary infrared observations based on the specifications for the Meteosat 3rd generation sounder as our baseline. We used a spectral response function similar to MTGS IRS, but expanded the spectral range to 650 to 2500 wave numbers, allowing for trade studies in the spectral domain. The red lines indicate the spectral range of MTGS. The channel selection for assimilation, indicated by red stars, converged on similar specifications using methods similar to how channels were selected for Ayres and Chris. The observations have a 4-kilometer spatial resolution and provide an hourly full-disk scan and observes channels in the CO2, window, and water vapor regions. The channel selection for assimilation provide a high-resolution profile of the atmosphere with weighting function peaks throughout the troposphere. We used the generated observations within the ISDA framework to examine the impact of geostationary infrared sounders with 2 experiments simulating July through September 2006. Both experiments assimilated all conventional and satellite observations, and the 4SAT experiment also assimilated GeoIRS observations using locations of those from international centers. This included the proposed GXS at 105 degrees west, MTG at 0 degrees, FY4A at 105 degrees east, and Himawari at 140 degrees east. All 4 of the simulated instruments are identical, with the only difference being their location. Differences between these 2 experiments in the representation of the atmosphere can be attributed to simulation of observations from these 4 geostationary IR instruments. For the analysis, the assimilation of GeoIRS observations led to multiple improvements in the simulation. Displayed here are the globally averaged, normalized root mean square differences, 4SAT minus control divided by the control, computed against the nature run, or truth. Blue indicates that the 4SAT experiment performs better. In all 3 figures, latitude is along the x-axis and pressure along the y-axis. Temperature is well observed by polar orbiters, but there are still improvements throughout the tropical tropospheric column, extending poleward beyond 30 degrees. The analyzed wind benefited from the added temporal information from the persistent observations from the geostationary satellite. This is one of the benefits of the geostationary orbit. The water vapor then benefited from both an improved analysis and a better transport by the wind. An improvement in the analysis leads directly to an improvement in the initial conditions used to generate forecasts. These figures show the normalized global average root mean square differences between the 4SAT and control experiments compared to the nature run for the duration of a 5-day forecast. Hatching indicates significance at the 90% level. In this case, the x-axis represents forecast time. As before, blue indicates an improvement in the 4SAT experiment compared to the control due to assimilation of geostationary IR sounders. Generally, the improvement is largest in the short to mid-range, with the largest improvements within the first 48 hours, and decreases with time as the differences in model physics between the data assimilation system and the nature run begin to dominate the solution. The forecast improvements dominate in the tropics, computed here as equatorward of 20 degrees, which is consistent with the larger number of observations near the equator from these geostationary instruments. Statistically significant improvements extend beyond 3 days, with the exception of the upper tropospheric temperature, which has an improvement for the first day before model differences between the data assimilation system and the nature run dominate the solution. Examining just the domain observed by GXS, roughly between 156 degrees west and 54 degrees west in longitude, and equatorward of 51 degrees in latitude, and encompassing the contiguous United States, the benefit of geostationary IR is apparent with statistically significant improvements in temperature, specific humidity, and zonal wind extending past 2 days. Another significant application of geostationary IR observations is the representation of tropical cyclones. One tropical cyclone that was present in the nature run, named AL03, formed within the Gulf of Mexico, traveled north, and made landfall along the Gulf Coast. We initialized forecasts of this system every 6 hours in both the control and the 4SAT experiments and compared their tracks. In particular, shortly after the formation of AL03, when it was rather weak, the forecast tracks between the 2 experiments diverged greatly. For instance, the 18Z forecast on the 7th of September and the control made landfall in the U.S. state of Florida, whereas the 4SAT experiment forecast track struck Mississippi, in line with the true track. For this forecast, The distance from the true landfall point was over 2 times greater in the control than in the 4SAT experiment. This figure shows the forecast track error averaged across all of the forecasts in kilometers. The number of forecasts used in the computation is shown along the bottom. The control experiment, shown in green, has a consistently higher error than the 4SAT experiment indicated in this figure in orange. This result shows an improved forecast track in the 4SAT experiment due to the assimilation of geostationary IR sounders throughout the 4-day lifespan of the storm. The largest difference is present in the early forecasts, before the storm was well developed in the nature run. This shows the potential for IR sounders in a geostationary orbit to improve tropical cyclone forecasts in the initial stages of their development. In summary, the GeoXO sounder is the U.S. response to the WMO's vision for a global ring of geostationary infrared sounders. The current plan is to have this instrument located at 105 degrees west. We evaluated the impact that can be expected from the addition of 4 IR sounders in a geostationary orbit in an ASI framework, and found that this results in an improvement in analysis skill. This translates to improved initial conditions for the subsequent forecasts and a predominant reduction of the error, especially in the initial 24 to 48 hours. The overall improvements in atmospheric representation contribute to better tropical cyclone forecast tracks, as was shown for a particular system present in the nature run. In general, persistent atmospheric sounding observations from a geostationary orbit have numerous beneficial applications and provide additional information for better decision-making. Today, I showed only the impacts from a global numerical weather prediction perspective. The high temporal frequency observations would have additional potential benefits for regional analysis and severe weather forecasting, among others. Thank you for taking the time to listen to my presentation today. If you have any questions, please feel free to contact me at my email address, erica.l.mcgrath-spangler@nasa.gov.